So let me give this example. Across a load, we're delivering a voltage that's equal to 120 volts cosine of 2 pi 60t minus 20 degrees. And it's in VRMS. By the way, the voltage coming out of your sockets, you might have heard we have 120 volts in the US. We don't. We really have 120 volts RMS. It would be 120 times the square root of 2 volts times cosine 2 pi 60t. We want to know what the current coming out of that socket is, and let's say it's 4 amps RMS. So it's going to be at the same frequency. Always has to be the same frequency regardless of what your load is. Different phase difference. And we'll measure that in amps RMS. All right. So I ask you to analyze this. Tell me everything you know. So first, what's the voltage measured in volts? Brian, you want to take a crack at that? It's going to be V of T equals, measured in volts versus RMS is going to be bigger in volts or smaller in volts?
Bigger.
Bigger. So it's 120 times, what's the multiplicative difference between volts and volts RMS for a sine wave?
Isn't it over, it's bigger.
It's the square root of
2.
2. So are you going to multiply it by the square root of 2 or divide it by the square root of 2 if you want it bigger?
If I want it bigger, I would multiply it.
You multiply it. So it's 120 times the square root of 2, and then the rest of it's unchanged.
Yep.
But now we're going to measure it in volts. And similarly, the current would be equal to 4 square root of 2, and the rest of it's the same. I'm going to make this instead of minus 10, plus 10, just to make these differences even larger. Okay, let's figure out what the apparent power is. What's the formula for apparent power?
VRMS times IRMS.
That's it. So the VRMS here is, now it's a scalar, it's not changing in time, so it's going to be just 120 times 4. Let me write the parts out. VRMS times IRMS equals 120 times 4 equals 480. And Ben, just finishing it up, what are the units on it?
VRMS.
That's the units on this. That's VRMS. And IRMS is the units on this, amps RMS. But what are the units on the 480? What's the units on apparent power?
VA.
VA. Don't call it Virginians. It's meant to be volt amps. Power factor. Grant, what's our power factor here? How do we determine what the power factor is?
Well, the P average is equal to S times PF.
That's true, but we want to calculate just the PF.
So
we're not interested in the S or the average power.
Just your cosine of the theta voltage minus theta current, I guess.
That's it. So it's going to be the cosine of, and it doesn't matter which we write first. We can write either one first.
Okay.
So that's going to give us, let's see, our theta I is 10 minus a negative 20. So it's going to be equal to cosine of 30, which Casey said is the same thing as cosine of minus 30. And you can just figure that out. It happens to be 0.866 square root of 3 over 2. And then you want to find out, let's see, is that leading or lagging? Ben Schreier. So leading or lagging?
Leading.
Right, exactly. The goal is to see what is theta I versus theta V. And theta I is 10 and theta V is minus 20. So because it's 10 is greater than minus 20, theta I is greater than theta V, and therefore we say it's leading. And a power expert would say would actually attach that onto the power factor designation. He would say the power factor is 0.866 leading. Let's see, what else can I possibly do to this? What's the average power?
It's your apparent power times your PF, which is just 0.866.
That's it. So it's whatever our apparent power is. And we've already said that's 480 times 0.866. So that works out to be about 417. And what are the units on that?
Watts.
Watts. not volt amps, which is apparent power, but watts, which is average power. Last thing, let's talk about what the load impedance has to be for this to be true. The load impedance, Z, I haven't drawn the circuit, but you can already figure out what that circuit is. It's equal to V over I, which is, we said V is 120, angle of -20, over I, which is 4 at an angle of 10. And notice that although I've drawn it in RMS, can you see that Ohm's law works equally well for RMS or non-RMS? Because if we draw it in RMS, the square root of 2's just cancel out. And so we have 120 over 4, which is 30. We have -20 minus 10, which is -30. And so that in rectangular notation, because we always write impedances in rectangular and we write sources in polar. In rectangular, this is 26 minus J, 15 ohms. DJ, if we took the 26, if this is our load, and if we want to convert that into resistors and inductors, what would our resistance be? We want to come up with a model for a load. It looks like some resistor. Oh, and this thing is going to look like something too. Is this reactive part? This negative J, is that going to be a capacitor or an inductor, TJ?
Passive.
Definitely a capacitor, because capacitors always have that negative amount. And DJ, just fill in for me, what's the resistor going to be, given this?
Wouldn't it be 26?
Just 26. And then that capacitor, we have to do a little bit of work for, right? Because we know that negative J over omega C is equal to this part, minus J 15. And we know that our omega from up at the top is equal to 2 pi 60. So from these two things, just finishing up quick, our capacitor has to be 177 microfarads, and that completes the problem.